Alright, multivariate gang. Today we are going to finish off this section. We are going to talk about the scalar triple product. Alright, if that sounds scary, that's because it kind of is. Only a little bit though. Not that bad. The scalar triple product is essentially a way in which we can multiply three vectors together. It's taking the dot product of a vector u and a cross product of vectors v and w. Okay, so there's the obvious way to do that, which is to cross v and w and to dot that with u, and that'll give you your result. But there's an easier way to do it. So we know that's the same as u dot the vector and you guys can verify me on this. I'm just going to go ahead and copy this out of your book. Vy vz wy wz I hat minus vx vz wx wz j hat plus vx vy wx wz j hat. All right, so that gives us ux times determinant vy vz wy wz minus uy times the determinant of vx vz wx wz plus uz times the determinant of vx vy wx wz, which, when you think about it, is the exact same as the matrix, the determinant of the matrix. Here, the determinant of the matrix ux, uy, uz, vx, vy, vz, wx, wy, wz. And if you need a second to comprehend the mind-blowingness of that, or if you want to verify me, go ahead and pause the video and do that. But we're going to keep moving on to example number 1. Find u, and there's a little dot there, it's just really small. Find u dot v cross u if u equals our favorite vector 1, 4, 7, v equals 2, 4, negative 3, and w equals negative 1, 0, and 4. All right, so we know that u dot v cross w, same as the determinant of the matrix 1, 4, 7, 2, 4, negative 5, nope, negative 3, negative 1, 0, 4. All right, so downs minus up, guys, downs minus up. All right, so, and that's 16. Plus 12 plus 0. Whoops. And then get rid of all those. Minus our ups. Negative 28. 0. And 32, which gives us 28 minus 4, which is 24. Looks really scary at the end of the day. Just a 3x3 determinant, algebra 2 stuff. Nothing to be too worried about. All right. So algebraic properties. of the scalar triple product. There are some properties that we can glean just from the nature of a determinant. Determinant of. All right. So our scalar triple product is the determinant of this matrix. Now we know that if we switch two rows of this matrix, that it makes that determinant negative. If I say switch this row, and I switch this row. All right. Now, if I switch two more rows, say if I switch this row and this row, the determinant becomes positive again. So we can then infer that this determinant where u's in the top, v's in the middle, and w's in the bottom is the same as the determinant where w's in the top, u's in the middle, and v's at the bottom. So we know that u dot v cross w is the exact same as w dot u cross v. And what do we do there? All we did was we moved everything to the right. We moved w to the right, which put it over here on the leftmost side. We moved v to the right, which put it over here in the rightmost side. And we moved v to the right, which put it here in the middle. And we can do that exact same thing again. And we get v dot w cross u. So we know that if we rotate these guys either to the left, or if we rotate them either to the right, or if we do the exact same thing but to the left, either way, if the dot and the cross stay the same and the letters move, it's the exact same. Now we can also focus on these guys, where if we know that u dot v cross w equals w dot u cross v, we know that the dot product is commutative, so that's the exact same as u cross v dot w, which means that u dot v cross w is the exact same as u cross w dot v. So if you switch where the dot and the cross are, that also gets you the exact same number. I think those are some fun facts. All right. Finally, a geometric interpretation of the scalar triple product. All right, so there's this shape. It's called the parallel piped. Or if you've got a vector u, vector v, vector w, there's this shape that is made up entirely of the parallelograms formed by these vectors. And the scalar triple product is the volume of this weird shape, the parallel piped. One more second to go ahead and get it drawn. How is that useful to us? Well, I don't imagine that you guys will have to take the volumes of very many parallel pi pads, but you'll probably have to take the volume of a couple. But the main use of this is that if we know that U dot V cross W, the parallel pi pad, I switched up my lettering. Sorry, guys. So I'm not entirely sure if it matters, but your book has it written like this one is U, this one is V, and that one is W. And I think... Oh, no, there is no significance to the order. I just told you guys that when I did this whole thing. Ignore me. We know that U dot V cross W is equal to the volume of this thing. The norm... No, not the absolute value of that statement is equal to V. So that's kind of helpful. But what if this is 0? What if our scalar triple product is 0? Well, how can the volume of a parallel pi pad be 0? How is that possible? Well, the only way that the volume of this thing can be 0 is if our vectors all lie in the same plane. Right? The only way that you can have a rectangular prism is if it has 0 height. If its volume can only be 0 if it has 0 height. So the only way that this guy can have 0 volume is if it's really like this guy. Just a couple of parallelograms smushed together. Nothing special. So if our scalar triple product is equal to 0, that means here, it's an if and only if. U, W, and V, and forgive me for not adding the fish hooks. I've gotten kind of lazy. Those three vectors are all coplanar. They all lie in the same plane. All right, that's it for the scalar triple product. And that's also it for this section. So you guys are now halfway done with chapter 11. Congratulations. I will see you all in the next